University of Washington. He studies dark matter and neutrino physics. He stole something out of the introductory physics demo storage for you today. So let's welcome Dr. Rybka.
Good evening. So I have to apologize. I made 3 big mistakes in coming here. I'm remedying them right now. So number 1 was obviously sound effects are key, but I did have a key to the demo lab, so I've got it's a bit lower 5, but I've got sound effects too. Mistake number 2. This is for a general audience. No technical terms. My title is The Search for Axion Dark Matter, and I've already violated that twice, so I have some explaining to do. So I can get to that. The third one I don't think I can remedy because it seems like the purpose of the speakers is to get you all in a position where you learn more about the universe. You step away from these knowing more about the universe, and I actually kind of want to make you learn to know less about the universe when I'm done. I can't really fix that. So sorry about that. Right, so yeah, I'm Rybka. This is the ADMX, the Axion dark matter experiment that I work on. Let's start with the dark matter part first. So what do I mean by dark matter? Well, you and I, we're basically the same, right? I mean, from a physics perspective, you and I are the same as we're the same as the chairs you're sitting on and the Earth, and we're pretty much the same. Oh, sorry, we're also pretty much the same as like the sun, other galaxies, all about the same stuff, right? We're all made out of atoms. So we're going to get along just fine. And we would be forgiven to think, okay, we've got this whole universe thing pretty well figured out, but there is some unfortunate messages from astronomy, and these messages come in at all scales, starting out at the scale of the entire universe. Yeah, I can't go into great detail about all these. If you look at the temperature of the sky, which is taking the temperature of the entire universe out there, you see bumps and lumps, and you compare these bumps and lumps to our understanding of how the universe formed, and you get that there's a lot of stuff out there that isn't made out of atoms, which is funny because we haven't really noticed things that weren't made out of atoms. So you look into a smaller scale, but still unimaginably huge, and that is of clusters of galaxies. And you can map out where the stuff is and where the stars are, and they're not in the same place. And with the star, and there's also, you could say, well, where is the gas, where is the dust? Well, it's not in where most of the stuff is, so there's some stuff out there that isn't stars, dust, gas, or anything else made out of atoms. Okay, let's look at a smaller scale. We can look at individual galaxies just like ours, and say, okay, so some of you have gone and have taken your early physics, you learned Kepler's laws, the planets moving around the sun, and you know how fast they ought to move given how far they are out. And you say, okay, a galaxy is a big clump of stars in the middle, and then some stars off to the side, and I ought to know how fast they're moving. No, you don't. You got it wrong. Kepler's law is not working. But they do work if you go back and say, well, what if there's a whole lot of stuff out there that's not with the stars, that's kind of diffusely spread out? Since we suspect there's stuff in, there's the entire universe, there's clusters of galaxies. Well, now this stuff has gotten into your galaxy. So the next scale down, from my perspective, is you go straight from the galaxy into the laboratory, and that's where we, as of yet, have no evidence. And yet, since this stuff is in galaxies just like ours, there's every reason to believe that in this room with us right now, there is stuff not made of atoms. Don't look behind you, but it's probably behind you. It's under your chair. When you go home, when you try and go to sleep, it's under your bed. It's in your closet. So it's stuff we know absolutely nothing about. So you know less already. Oh, there's a lot more of it than us. So all right. So you already know less about the universe than we started. I'm not even going to mention beyond dark energy, which there's much more of, and it's even more mysterious. Okay, great. To which the enterprising physicist says, "Good. Let's find it, bottle it, and sell it." To do that, you've got to have a guess about what it's made of. And for this, you've got to come up with some ideas of what the particle ought to be called. The one I like is called the axion. And I took this slide from one of the UW physicists, UW theorists here, Ann Nelson, because I really liked it. The implication is that there's a whole lot of theories for different dark matter out there, and she was making the argument that if you want your theory to be natural and elegant, for whatever that means, you really ought to pick the theory with a theory with dark matter axions. I'll give you a very brief story about the axion. So if you look at the stuff that holds nucleons together, it's the stuff that makes the center of the atom hold together, and you look at the force that makes it fall apart, the strong force and the weak force, they behave very differently, or rather, let's see, so the strong force, the stuff that holds it together, looks basically the same going forward or backwards in time, and yet the stuff that makes these nuclei fall apart looks very different going forwards and backwards in time. And this ends up being very strange, because if you go and take all your measurements, and you write down all the best equations we've got, this means there's two things that are canceling out, not like, just mostly canceling out. They cancel out with 10 zeros, or it's basically that if you divide these two things, you get 1 point and then 10 zeros at least to confirm our measurements, which is very unusual, and so you kind of need an explanation. And the explanation is something called Peccei-Quinn symmetry, which blah, 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 and suddenly you've made a new particle. That's really, the stuff in the middle, it's important and interesting, but not for this point. There's a new particle of the axion, and interestingly enough, is if you have this axion, then in the early universe, you produce a whole lot of this particle and it's still around. That sounds like something we need. So, axion dark matter, we want to find it. Now, how do you find it? Because we know that if dark matter is, if dark matter is in this room and yet we haven't detected it yet, it must be really hard to detect. It couples extremely weakly to electromagnetism. What does that mean? That means that dark matter and light can touch each other only just a little bit. How do you build an experiment to look for something that's only very, very weakly interacting like this? And in the case with axions, I have before me what is mathematically identical to what you write down when you're trying to solve this equation. I'd be writing down Maxwell's equations and solving for electromagnetism, but in this case we're going to do it with sound waves. So, on the right-hand side, we have the axion field. It's a tuning fork. And the left-hand side, we have an electromagnetic resonator, which is a big tin can. Well, it's like a copper. You'll see it later. But in this case, it's also represented by a tuning fork. And the extremely weak interaction between dark matter and normal matter is modeled here by the fact that these aren't touching. They're just kind of these two boxes pointing at each other. So let's see if I can set this up. Now, dark matter is always all around us, so I should hit the tuning fork so it's always going. There it's going. So there you go. So we excited energy in our dark matter, and because this tuning fork here was exactly tuned to the frequency of that tuning fork, we could transfer the energy even though it's just very weak, just through the sound waves between the two. Now, of course, if I do this with the this tuning fork detuned, so I just move that weight. No good. So, let us go on. That's it. That's how this works. That's how this works. Right? This is a tuning fork. This is a tuning fork, but it's in electromagnetism. We have to tune it exactly to the frequency the axion is moving back and forth with. We don't know that frequency. Our best minds are trying to predict it. They give us, well, it's bigger than like 100 megahertz, and it's smaller than maybe 100 gigahertz. So, there's a lot of stuff that's covered in there. There's cell phones, there's Wi-Fi, all that. So there's a lot of building that goes on in my lab. This is starting, this right here is about 800 megahertz, and we're working our way upwards. And so I'm pleased to say this is over at SEMPA at UW here, and we are operating this experiment. So we just started last year operating with the sensitivity needed to find dark matter, but we don't know where it is, so here we are sitting tuning this thing. Tick, 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 tick. It's very slow, because you have to listen for the whole, but it really is, you're just listening for a tone. And so it may be that this year, next year, the year after, those of you here for CUWiP, This is a great thing to get in graduate school because, you know, just any day you hit the right frequency, bam, you got a dark matter. Bottle and selling it. Well, maybe not bottle and sell it, but I will tell you a whole lot more about astrophysics and the universe we're made in, the universe that we're living in. So I'll conclude with, everything you thought you knew about the universe is actually only a small part of it, sorry. But we're working on that. Thank you.